Today's learning goal is to describe the causes and consequences of atmospheric pollution. And we're going to do this by continuing on with part 2 of the atmospheric pollution notes. We are going to begin right underneath the evaluation of management strategies data table where it says acid rain. Before we begin, let's talk just briefly about the pH scale for measuring acidity. Traditionally, the pH scale goes from 0 to 14, although you can go below 0 and above 14 in extreme circumstances. On that scale, a 7 is completely neutral. Any number below 7 is acidic, and a number above 7 is basic. However, the closer you get to 0, the stronger your acidic solution tends to be, and the closer you get to 14, the stronger your basic solution tends to be. It's also important to note that the pH scale is what we call a logarithmic scale. That means that for each 1-point jump on the pH scale, you have an increase or decrease of a multiple of 10. For example, a move from 7, which is neutral, to 6, which is mildly acidic, means that your hydrogen ion concentration has increased by 10 times. Also, a move from 6 to 5 pH is the same thing. Your hydrogen ion concentration increases by a multiple of 10. However, a move from 7 to 5 represents a 100 times increase in your hydrogen ion concentration. From 7 to 6 is 10, and you multiply that by from 6 to 5, which is also 10. So 10 times 10 gives you 100x. So a move from 7 all the way down to 4 represents a 1,000 times increase in your hydrogen ion concentration. A move from 7 to 3 is a 10,000 times increase in your hydrogen ion concentration, and so on. So rain is naturally slightly acidic. It has a pH of 5.6, and this is because of the carbon dioxide in the atmosphere, which reacts with water and oxygen in the air, and this produces an acid that we call carbonic acid, which isn't a huge deal because it is a weak acid. But when sulfur and nitrogen oxides dissolve in the rain, they form sulfuric and nitric acids, which are much stronger acids. These can result in the formation of a very low pH. We're going to talk a lot more about sulfur and nitrogen oxides in a little bit, so I'm not going to get into those super deep right now. But we are going to take a quick look at this diagram. Over here on the left side bank of this river, we have a depiction of some factories and possibly a power plant or two. And we have the production of sulfur dioxide, SO2, and nitrogen oxides. A lot of times we call this NOx, being released into the atmosphere. Winds are carrying these dangerous chemicals downstream, and the gases then react with water in the atmosphere as well as oxygen to form acid rain, which is deposited down onto the surface of the earth, which can then damage things such as plants, anything that lives in a river or stream, and also it can erode and weather rocks and stone on Earth's surface. So acid deposition is the general term for acid coming down from the air, and we can divide acid deposition into two categories. We have wet deposition, which is when we have acidic precipitation, for example, rain or snow, and then we can have dry deposition, which is just what it sounds like. You have dry particles such as ash or simply acidic gases that have formed without being mixed with water. So we should make sure that we can outline in general terms how acid rain forms and is deposited. Let's talk about some of the sources of the chemicals that cause acid rain. We're going to start here with sulfur. More specifically, we're talking about sulfur dioxide, which is SO2. And this can come from natural sources, for example, volcanic eruptions. However, this is a small percentage of the sulfur dioxide that is released into the atmosphere, and it doesn't cause a big problem. Where we come into a significant problem is when we have anthropogenic sources of sulfur dioxide, and this comes from fossil fuel combustion. And primarily, sulfur dioxide is a much bigger problem with coal burning power plants than it is with oil and gasoline combustion. Although sulfur dioxide is produced by combustion of both coal and oil products, the coal burning power plants are a much larger issue with your sulfur dioxide pollution. So let's talk about the sources of atmospheric nitrogen oxides. A lot of times this is simply called NOx. What we're talking about here with NOx is primarily two chemical compounds. We're talking about nitric oxide, which is NO. Sometimes it's called nitrogen monoxide. And then we have NO2, which is called nitrogen dioxide. So both of those compounds together, we call it NOx. Natural sources of nitrogen oxides include the formation of NOx via lightning strikes in the atmosphere. It doesn't produce a significant amount of nitrogen oxides. Again, when we run into the problems is when we have NOx being formed from anthropogenic activities. For example, the combustion of fossil fuels. So while sulfur dioxide was primarily formed in the combustion of coal in coal-powered power plants, that's not so much the case in NOx. NOx primarily comes from the combustion of fossil fuels in traditional automobiles. And the source of nitrogen for the creation of NOx is not in the fuel, it's actually in the atmosphere. We've talked about how the amount of nitrogen making up the atmosphere is roughly 76%. So as internal combustion engines intake air from the atmosphere, in the cylinders of those engines, you have intense heat and pressure, which is required to propel the car forward. The reaction inside the cylinders of the internal combustion engine is what actually produces your NOx molecules. And one more thing here, it's not actually the sulfur dioxide or the NOx particles that result in the drop in pH in acid rain. It's actually derivatives of those chemicals that cause those water particles in the atmosphere to become acidic. The sulfur dioxide, through a set of complex photochemical reactions, are actually converted to sulfuric acid as they react with water and oxygen in the atmosphere, and the NOx molecules are likewise converted to nitric acid. So it's the sulfuric acid and the nitric acid that actually causes that significant drop from 5.6 to between 1 and 3 on the pH scale, which is what causes your acid rain. So here we have a couple pie charts. We've got sulfur dioxide here on the left and the sources contributing to the sulfur dioxide in the atmosphere broken up as slices on the pie chart. And over here we have nitrogen oxides and the sources contributing to the increase of nitrogen oxides in the atmosphere over here on the right. And as you can see, the sulfur dioxide is mainly produced by utilities. So what we're talking about here is coal-fired power plants. And the NOx over here on the right, the largest slice is yellow, which represents transportation. And of course, we talked about this being from the internal combustion engine. And you can pause the video if you want to and take a look at some of these other sources, these other auxiliary sources of these two molecules in the atmosphere. We should make sure that we can list the main sources of the pollutants. These are sulfur dioxide and your NOx molecules that cause acid rain. So let's take a look at some of the effects of acid rain. We have some direct effects, and just in general, many biological processes do not perform too well in acidic conditions. And the reason for this is that many of the enzymes that are required for life do not react correctly when you have a high hydrogen ion concentration, which is what causes something to be acidic. And a good example of this that we all know about that we might not have thought about is the fact that vinegar is used to preserve many foods. If you submerge a food in vinegar, you're not going to get any mold or bacterial growth on it, because the development of those organisms is going to be inhibited by the high hydrogen ion concentration. And like we talked about, many of the enzymes that are required for life do not perform correctly when you have that situation. So likewise, if you have sensitive organisms that are developing in acidic conditions, they're not going to develop correctly. This is exemplified by taking a look at embryonic development of fish. There have been many well-documented examples of fish stocks in inland lakes that have been depleted because the embryos of those fish cannot develop in increased acidic conditions. This was a pretty pronounced problem in the United States and Canada between the years of about 1965 and 1985 to 1990. There was increased death and a reduction in biodiversity in many lakes and ponds due to the acidic pH caused by acid rain. Acid rain can also contribute to plant death by thinning of the waxy cuticle that coats needles and leaves. The purpose of this waxy cuticle is to decrease water loss in high temperatures. And without it, you have plants that can become dehydrated much easier. Acid rain also damages chlorophyll, which is the green photosynthetic pigment in many plants. And we should make sure that we can outline some of these direct effects of acid rain. What we've got here on this slide is some of the damage caused by acid rain. You can see a normal conifer tree branch here on the right compared to one that has been damaged by acid rain here on the left. You can see the damage to these leaves of these plants here on the right caused by acid rain. And over here on the left, we have damage to an entire area of the forest, which was in a boggy location that saw its pH drop as a result of acid rain. Let's take a look at some indirect effects of acid rain. So we're going to start here by talking about toxicity or toxic effects. And what we see here, a big problem, is increased solubility of metal ions such as aluminum, which is toxic to many living things. And what happens is you have aluminum that is stored in rocks or soil, and this is leached out as a result of the increased hydrogen ion concentration caused by that acid rain. So the aluminum from the soil and the rocks eventually ends up in streams and rivers, and this can be particularly damaging to fish that live in these bodies of water. At even low concentrations, aluminum disrupts the fish's ability to regulate the amount of salt and water in its body. So this causes the fish to have a much more difficult time as it tries to intake oxygen from the water and also salt particles. So the fish either suffocate to death because they can't get enough oxygen, or the salt content in their bodies is slowly lowered, which can also lead to death. Another indirect negative effect of acid rain is nutrient loss. So soil particles can't retain essential minerals such as calcium, magnesium, and potassium. So basically what's happening here is these are essential to organisms that depend on these minerals in the soil, for example, plants and bacteria, because what happens is the acid rain increases the solubility of these ions, and it causes them to be leached out deeper into the soil, so they're not available up there by the surface where the plants and bacteria need them to grow. And we should make sure that we can outline some of these indirect effects of acid rain deposition. So let's talk about some of the societal effects of increased acid rain deposition. We have damage to buildings, roofs, and especially things made of limestone, which is calcium carbonate. Now, any carbonate is a weak to moderate base. So what happens when acid rain hits limestone, which is calcium carbonate, is you have a neutralization reaction, and this can dissolve any structures that are created using limestone. Now, unfortunately, many historically significant sculptures and statues are made of limestone, and so a lot of features on intricate statues and sculptures can be lost in a relatively short span of time because of the effects of acid rain. Also, you can have dry deposition, which, remember, is the deposition of acids in the atmosphere by means of things such as ash or even dust particles. And if these acidic particles are inhaled, this can cause illness or death, especially after prolonged exposure. So again, we should make sure that we can outline some of these societal effects of acid rain. So let's take a closer look at the actual deposition of acid rain. And most areas of acid rain deposition are actually downwind of the pollution sources. Dry deposition actually occurs close to the source of the sulfur dioxide and NOx particles. This is because oftentimes the SO2 and NOx particles are simply released up into the atmosphere, and because of wind currents, they flow back down to the surface of the earth. Now, wet deposition occurs at slightly longer distances from the sources of the pollutants. And what you have is the sulfuric acid and the nitric acid, which form as a result of those primary pollutants, actually travels significant distances in the clouds before it's deposited as precipitation. A couple examples here of acid rain caused by wet deposition. Canadian forests in the eastern part of Canada were becoming damaged by coal-fired power plants in the Midwest states of the United States. Also, Scandinavian and German forests were damaged by British coal power plants. And so if we look at a map here, we can see some of the patterns emerge that we just talked about. And one of the things I want you guys to take a look at is over here on the eastern part of Canada and the eastern region of the United States. What happened here is there were many coal-fired power plants that used coal that had a high sulfur content, and these were located in the Midwest region here in states such as Indiana, Kentucky, and Ohio. And these power plants released a significant amount of sulfur dioxide, which was then carried via the prevailing winds to the New England states over here, where it would be deposited as sulfuric acid and thus cause acid rain in the New England states. So beginning in the mid to late 1980s, a consortium of these New England states brought forth several lawsuits against the Midwestern states. Also, the EPA was sued because they could prove that the source of the acid rain that was coming down over here was actually over here in the Midwest. And if we just sit here and think about this for a second, what is the purpose of these tall smokestacks that you see protruding from industrial facilities? And we also see them oftentimes coming out of coal-fired power plants. It's to move that pollution that's produced by those facilities up away from ground level. And what happens is then it's carried downwind to the neighbors of those communities. So this is how we see those effects manifesting, not in the place where they're produced, but where the prevailing winds carry them to. So we should make sure we can describe the current distribution pattern of damage from acid rain. We're going to move on here and take a look at some management strategies for acid rain. And we're going to begin with ways to alter the human activity that causes the release of sulfur dioxide and NOx emissions, or we'll call it replace those chemicals with something better. So we can switch to, of course, renewable energy sources, which will reduce fossil fuel use. We can increase the energy efficiency of things like light bulbs and appliances. So even if we still are relying on coal-fired power plants to produce the energy for those things, at least we're using less energy. We can attempt to utilize more methods of public transportation and thus rely on fewer automobiles on the road. We can use low sulfur fuels. For example, you can get ultra low sulfur diesel fuels and low sulfur coal. And now we're going to take a look at ways to regulate the emission of SO2 and NOx molecules. We're going to begin here by talking about scrubbers, which can be installed at the top of those damaging smokestacks from coal-fired power plants. And these are machines that can actually trap the sulfur dioxide particles as they are released in the gases that are emitted from the top of smokestacks. The problem with these is that they tend to be expensive, so the power plants have been reluctant to install them. And we've already talked about the catalytic converter, which is a device installed on the exhaust system of automobiles. And this is used to trap a lot of those NOx emissions, and they're required by law in the United States, Canada, and many parts of Europe. Now we'll take a look at some ways to clean up and restore areas that have been damaged by acid rain. So a procedure utilized early on when they started noticing the decline in fish stocks in some of these inland lakes affected by acid rain is that they would go around and they would add limestone to the acidified lakes and streams. So this is kind of a quick fix mentality. You're not actually solving the problem, you're trying to mitigate the effects after the fact. But this was widely used all the way from the 60s to the late 80s. And as we talked about, limestone is a moderate base. So when you combine that with the acid, a neutralization reaction takes place, and it tends to increase the lowered pH that was seen in many of these devastated lakes. So the limestone, which was made of calcium carbonate, actually acted as a buffer on the impact of the acids. We should make sure that we're able to discuss some of the pros and cons of these management strategies used for acid rain. All right, that's the end of the notes. Don't forget your questions in the margin and your summary there at the end.